lecture and the lecture after that is talk specifically about simple things we can do to control that. And what's the underlying technology, how does it work? We'll be talking specifically about that. Okay, then we'll move on and we'll talk about other topics, but we'll keep coming back and saying that this is a concurrent operation. Okay. So how should it run? How should it run? We would like for it to run like this. Thread 1 runs I++, and then thread 2 runs it. Or thread 2 runs it to completion, and then thread 1 runs it, right? We need them to be ordered or synchronized. Okay, we need them to be synchronized so that they occur one before the other. Whichever order it's in general, we don't care. Okay, and we're just going to assume in this class that we don't care about the ordering, just that they don't overlap. Because it's the overlap that kills us. It's not the fact that both occur, it's that they both try to occur at the same time. Okay. It's the fact that they try to occur at the same time. The fact they try to occur concurrently. We need to put them in order or serialize or linearize these operations so they're occurring like in a straight line. And that's the way you write your code, isn't it? We just say, do this instruction followed by this instruction followed by this instruction followed by this instruction. We typically don't go in there and go, as many threads as need to do this instruction. Oh, this one you have to line up one behind another. You can't do that all at the same time. And we don't think that way. But in a concurrent world, we have to start thinking about that. So the question is, how do we think about it? And the way to think about it is, this problem can only occur with shared data. It's not that we're sharing code, it's that the code is accessing shared data. If it's accessing thread private data, we can be in the same code running it all day long because it's looking at different memory addresses, isn't it? It's only when we're looking at the same locations in physical memory that things go bad. Okay? So concurrency control is really about data access control. Okay? It's around the data. We'll call it a critical section will be a piece of code where we access shared data. Okay? We're not guaranteed to access it at the same time, it's just that it could happen. And that data is shared. We typically consider that global data out of the heap someplace. Okay? So we need to be aware of where the data is stored, and then any code that manipulates that is considered a critical section. So if you have 10 different pieces of code spread around in your program at different places, and they all access the same shared piece of data, collectively they're the critical section. It's not just the one chunk of code that's manipulating it. That's not one critical section. And then the code over here that's manipulating the same data, that's not a separate critical section. They're the same. They're both critical sections for the same piece of data. We're going to see that in XV6 because we're going to be using the p-table data structure a lot. And in order to use that, we're going to have to control concurrency, and we're going to do that with a lock. Okay? Lock is going to be the first structure that we study.
So where's the critical section located, hardware-wise?
Hardware-wise?
Well, yeah, like in the CPU, is that what you're saying?
Well, the critical section is code that's being executed where that code accesses a shared variable.
It's not necessarily a section.
It's a section of the code.
Okay.
Okay, so it's in the process. And what happens is because we're switching because of these interrupts, while we're manipulating one and we've loaded, remember we do a thread switch or a context switch, we take the values of the registers and we store them in memory, don't we? So we've got a piece of data from memory, but we're manipulating it inside a register. We get a context switch, those registers get saved, the new thread comes along, its registers get loaded. It doesn't have our updated version of that data. So it goes off to memory, gets it again. And now we have the same piece of data in two different contexts, two different thread contexts. And now, that's the problem. Okay, because both of them think they've updated them, but the end result is after 2 threads update it, the final result will only be 1 update. Instead of I equals I plus 2, we have I equals I plus 1.
Okay, the name section is throwing me off a little bit.
I'm not trying to say, but let's say block.
I get what you're saying, okay.
Okay, and it might be 4 lines of code. It could be an entire function. It's just a contiguous, a group of lines of, say, source code here. But anytime that shared data, let's say the data structure is called D. Okay, some data structure D. Every place that's accessed within your program, since it's global data, all of those comprise the critical section for the piece of data called D. Because if any of those are run at the same time, we could corrupt D. Okay? So it's not this little piece of code here where it accesses D is the critical section. No, it's a critical section. The critical section for D is all of those combined. So you don't just say, hey, I'm accessing D here. I'll just use concurrency control. I'll use a lock. But over there, I don't think so. All right? It's not the way it works. If you have a current data structure, you have to use concurrency control. There's a technique we'll see in a second, or next time, one or the other. We'll talk about different types of locks. And there's ways that the programming language can enforce it, so you don't have to remember to do locking. There's almost no programming languages that support it. Okay, but it's the type we want. We want to say, when I access I don't care if it's global or not. My thread, when I access it, I'm the only one that can access it right now. Okay? The language should enforce that. That's how we write our code. But that's not the way the world works. Okay? If you ever found that you write your code the way you want it to work, not the way it actually works? Did anyone ever notice that? Okay? Do as I mean, not as I say. You ever heard that one? Okay, so we've just shown 2 different ways in which I++ could be executed. Those are just 2 of the possible ways. Unless we take very special pains, each time we go through there, we will get one of the possible ways that it could work. Which means sometimes it will work, and sometimes it won't. Okay? Do you guys know who Clint Eastwood is? So if I say, do you feel lucky, punk? Okay? So concurrency bugs are frustrating because they're not deterministic. You have a bug, but it only shows up every once in a while. Isn't this fun? Okay? Welcome to the real world of programming. Okay? Almost all the programming you're going to do in your professional career is going to be concurrent. Okay? C# is concurrent, Microsoft C is concurrent. Okay? Almost everything is concurrent these days. Everything's multi-threaded. So we have to be aware of this. Any questions before we step on? Okay. Now, I got everybody's attention. Is anyone starting to sweat just a little bit about this? Well, the rest of this lecture and the next 2 lectures are how to go about making it so these concurrency bugs, not that they won't occur often, they won't occur at all. How do we control concurrency so that we can avoid concurrency bugs? That's what we're going to talk about. Operating systems have always been concurrent because they switch from process to process to process. So inside the operating system, there's all these shared data structures. Okay? And every time there's an interrupt, it's going to be doing things for a different process. If it's got more than one CPU, like we have in XV6, things could be done in parallel or they could be done concurrently. So, and the full word of concurrency is parallel or appears to be parallel. We get both types in XV6. That's why we don't have to do multi-threading, because our operating system already has it. And that's why we teach it in this course, is because it's been in operating systems forever, and we know how to teach it very, very well there. Okay. So, does anybody take a look at the concurrency introductory chapter in the OSTEP book? It's not that long. What is it, about 8-10 pages? And most of it's an extended example. And it's a particularly fine example. Okay? And I encourage you to look at it. But at the very end of it, it has this statement. Okay? What's happening when we're trying, with multiple threads trying to access that data at the same time, it's called a race condition. Okay? It's one of those things, I got to it first. You know, if we have concurrency control, whoever gets to it first should win, right? But if we don't have concurrency control, we can rush in and 2 people can grab it, 2 threads can grab it at the same time, 100 threads could grab it at the same time. So we have to control that. This unbounded access to this piece of data is called a race condition. Okay? So we have this idea of a race condition. Okay? Race condition is the traditional term. The industry is starting to use the phrase data race. Okay? I don't care which one you use. I know that they're both the same. Pick which one makes the most sense to you. Okay? Most of our problems are going to occur because of the context switch that's associated with a particular type of interrupt. Okay? If we're on a massively parallel machine, they can occur just because 2 threads are running on different CPUs simultaneously, but all our processes are single-threaded, so we're using a simplified view at this point. Okay? So, because we can get a different result each time, our operation is now called non-deterministic. The book likes to call it indeterministic, but that book's the only place I've ever seen that phrase. Okay? Now, one of the nice things about computers is that they're deterministic. That's why we use them, right? If we always have the same data, the same context, the same global state, at the same location, and we run the same instructions, we should always get the same answer, shouldn't we? That's what determinism is. Okay? Mathematics is deterministic. All right? How many of you have ever had 1 + 1 = 2? Okay, good. Some people are awake. 1 + 1 = 3. 1 + 1 = 1/2. I can show you a proof. But that can only happen if something goes wrong. Okay? Mathematics is deterministic. 1 + 1 will always be 2. Okay? I++ called twice should always be I = I + 2. Okay? Otherwise, we go through, sometimes it's 2, sometimes it's 1. Isn't this wonderful? Okay. If you go back to that example where we had those interrupts, you'll see that because of concurrency, we don't have one possible outcome of that run of code. We actually have 2, one for each thread. Okay. So I++ could wind up equaling I + 1, or when we call it twice, call I ++ twice, it could wind up being I = I + 1 or I = I + 2. There's no way for it to equal I = I + 3 though. Or just have it equal I at the end. Okay? So if we start with, at the beginning of that, if we had 3 as our example, we expect 5 at the end because we're doing it twice. But it turns out we can also have it before. Now, there's a type of concurrency issue that we're not going to talk about where it turns out I could be 75 million after I++ because of a concurrency bug. We're not going to talk about that. There's a lot of theory behind it. In practice, it doesn't happen. But theoretically, it could happen.
What happens if one section of code tries to place a lock when there's already a lock?
we're going to talk about locks. We haven't gotten to locks just yet.
Okay.
So when we get to locks, we're going to talk about that.
Okay.
Okay. And there's several things that could happen. Most of them are good. Most. Okay. So it turns out that, and in fact, in XV6, all of our concurrency bugs occur because of the scheduler, because of the interrupt. Okay, and that's why we're using XV6. We don't have to worry about the many other different ways that it could occur. We've simplified it. It's only going to be the scheduler. So the scheduler's job is to pick the next task to run. So only the scheduler can move from thread 1 to thread 2. We need the scheduler to do that. Okay? So the scheduler is the problem. Okay? The scheduler causes the problem to manifest. The real problem is shared data. Because the scheduler doesn't look at your code and suddenly go, oh, it would be a good time to mess with you. Although we're going to pretend that it does. Okay? I like to call it the malicious scheduler. The goal here now, we're going to assume always that the scheduler is out to get us. Because it's an asynchronous process. We don't know when the scheduler is going to run, so it could happen at the best possible time or the worst possible time. And in programming, we program defensively, hopefully. So we need to program as though it will always occur at the worst possible time. That's what we need to do. So we're going to assume that the malicious scheduler knows exactly when doing a context switch would hurt us. But I'm going to show you how to program so the malicious scheduler we don't have to worry about anymore. It's like, you can be malicious all you want, scheduler. Yeah. Screw you, Bucky. Right? Okay? We're just going to say, you can do whatever you want. You can be malicious all you want, but you can't hurt me. You can't cause that race condition and corrupted state. Because we're going to get rid of the race condition. Okay? You guys with me? Mm-hmm. All right?